Hello everybody, it's Tarun. Welcome to your fourth tutorial in Signal System and Control course. So we have completed Unit 1 and in this tutorial I'll start Unit 2, which is Linear Time Invariant Systems. So in this unit what we'll do, we'll learn about discrete time linear LTI systems and continuous time LTI systems, which is a representation of convolution sum and convolution integral respectively, and some properties of LTI systems and differential and difference equation representations, okay, which is also called as block diagram representation. So these are the important things in this unit, or I would say that this whole unit is quite important regarding the next units which are to come. So keep focus, keep concentrating on the contents of this unit. So let's move forward with the convolution sum. So, okay, what is convolution sum? Let's see. Okay. Well, first of all, what is LTI system? Any system which follows the linearity property and time invariant property is called a LTI system. So in the discrete time LTI systems, we are talking about a particular type of system which is the convolution sum. Okay. So in this type of system, we are trying to use the linearity and time invariance to obtain some characterization of discrete time systems. Okay. So the observation for this convolution sum is that any signal can be composed as a superposition of time shifted unit impulses, which is delta n in case of discrete, okay, which is also called sampling or shifting property of unit impulse. So this is the convolution sum formula. Okay, memorize this formula because it will be used many times. So what does this say? That the signal xn is equal to summation minus infinity to infinity x of k and delta n of minus k. Okay, so now let's understand this better with the help of an example. You are given this function xn, okay, and if I multiply it with delta n plus 1 and with the x of minus 1, so x of minus 1 will be this, okay, and delta of n plus 1 will be 1 at x at n is equal to minus 1, and x of 0 into delta n will be the value of xn at 0 and 1 with which comes from delta n at n equals to 0, then x of 1 delta n of minus 1. So you can see that when I sum these three individuals, okay, when I sum all these three, okay, then I'll get this signal. So you can see that xn equals to x of minus 1 delta n plus 1 plus x of 0 into delta n plus x of 1 into delta of n minus 1. So this was the observation which I told you, that any signal can be represented as superposition of unit impulses. Okay. So unit step function is also an example of this type of observation, where we are summing the delta function or the unit impulse function from 0 to infinity to get un. Okay. So now let's see some LTI system characterizations. Okay, I am defining a function delta n minus k, which is when taken as input will give the output hk of n. Okay, I have defined it. So by the linearity property, if xn is this signal and it produces output yn, so it will change corresponding to xk hk of n, because I have defined delta n minus k to h of hk of n. And for time invariant property, you can also verify it, and the impulse response is denoted by this for the function I have defined. So if these are the properties for any system I have defined, then the convolution sum is equal to y of n equals to sigma k is equal to minus infinity to infinity x of k h of n minus k. Okay, and the symbolic representation for convolution is by asterisk symbol. Y of n is equal to x of n star asterisk h of n. Okay, so let's see with an example and let's understand it. I have input xn equals to delta n plus 2 delta n minus 1 plus 3 delta n minus 2, and h of n is 2 delta n plus delta of n minus 1. So if I want to plot the graph of xn, then it will be here at 0 at 1 and 1 at 0 and 2 at 1 and then 3 at 2. Okay, and for impulse response it will be 2 at 0 and 1 at 1. Okay, so you can see that this is the graphical representation of xn and hn. So let's find the convolution sum of these two signals. So this is the convolution formula, and since the x of n is lying between 0 and 2, so we can simplify for x of k is equal to 0 for k less than 0 and k greater than 2. So our y of n will be defined between k is equal to 0 to 2. Okay, so this is a causal system because h of n is equal to 0 for n less than 0 and y of n is equal to 0 for n less than 0. So now let's see for n greater than or equal to 0. First let's see what is y0. For y0, here I have put the value of n equal to 0, and this function will become x of k into h of minus k, where k is equal to 0 to 2. So if I put the value of k other than 0, then the h of minus 1 and h of minus 2 do not exist, so they will not come into account. So if I put 0 here, then it will become x of 0 into h of 0, and with this function, if you try to find out x of 0, it is equal to 1, and in h of n it is equal to 2, so the multiplication is 2. Now let's see y1. So here I have put h of n is equal to 1, and it will become h of 1 minus k. So when I put k is equal to 0, it will become x of 0 and h of 1, and when I put k is equal to 1, it will become x of 1 and h of 0, and if I try to put k is equal to 2, then this term h of 1 minus k will become h of minus 1, which will not exist. So when I calculate x of 0 into h of 1 plus x of 1 into h of 0, then it is equal to 5. Okay, so for y of 2, so similar procedure you can follow for this and you will get the answer 8. Similarly for y of 3. Okay, and if you check for n greater than equals to n greater than 3, then you will know that h of n minus k is equal to 0, implies that y of n is equals to 0. Okay, so this was how you have calculated the convolution sum. So let's see the graphical interpretation of how to use the convolution sum. Okay, plot both x of k and h of k. Okay, and shift h of minus and time reverse the function h of k. So this was the function h of k earlier. So first you need to time reverse it and convert it into h of minus k, and then shift of h of minus k by n. Okay, so if I shift h of minus k by n, then it will delay the function. So for the previous example, this is x of k and this is h of k. So if I convert it, reverse it and then shift it by n minus k, and then I can solve the convolution with the help of graphical representation also. So how can I do that? Let's see. This is x of k, h of k. So if I just wait. So if I make the function graph of h of minus k, then the function will look like this. Okay, and it will be at 0 and it will be at minus 1, and this is of h of minus k. Okay, so now if I make the graph of h of n minus k, okay, so the graph will look like this. Okay, so this is the case when n is less than 0. Okay, so if n is greater than 0, then the graph will look like this. Okay, so when I convolute these, what does the convolution mean? That for, let's see, for n equals to 0, so if I put n equals to 0, then this will become h of minus k only, and h of minus k has a value at minus 1 and at 0. So if I multiply it with x of k, then we multiply the respective terms at the x-axis. So minus 1, the term of h of k, h of minus k at minus 1 will be multiplied with the minus 1 term of the x of k. Okay, so it is 0, so it will become 0, and now the 0th term will be multiplied by the 0th value of x of k. So it will look like this. Okay, and you will get y of 0 is equal to 1. Okay, oh, sorry, y of 0 equals to 2. Okay, similarly you can do for the y of 1, y of 2 and y of 3. Okay, so this was all about convolution sum. For further examples you can look into the book, or I will provide the assignment after this unit. There are questions which you can solve to create to freshen up more the concepts of the convolution sum. So now let's move forward to the next topic, which is the convolution integral. So the difference between convolution integral and convolution sum is that the convolution sum was for discrete time systems, and the convolution integral is for continuous time LTI systems. So this is similar. In discrete time we took the input xn and produced output yn with the help of impulse response hn. Okay, the h function is called impulse response. Okay, but in continuous time we will take xt as input and produce our yt as output with the impulse response h of t. Okay, so this is the observation that any continuous time signal can also be represented as superposition of infinitesimal, which is very small, time shifted continuous time unit impulses. Okay, so this is unit impulse which is time shifted, and their summation, which is integration in this case, can represent as any signal. Okay, so let's see it with an example. The unit step function, okay, u of t, is represented with the help of unit impulse, which is represented as minus infinity to t integration delta t dt. Okay, or it can be represented as this also, time shifted version. What we can do to do this: replace tau is equal to u. Okay, sorry, t minus, just wait, replace t minus tau with u. Okay, so if I differentiate it, then minus d tau is equal to du. Okay, so if I replace this, then I'll get this term, or you can do vice versa also. So this was something with the help of integration you can solve. Okay, so the characterization of LTI system, let's check that. I have defined ht as tau of t as delta t minus tau, sorry, and it follows the linearity property. Okay, and it is also time invariant, and its impulse response is represented with this term. Okay, so the convolution integral will have this formula. Okay, this is also important, as the convolution sum is important. So just it is just similar to convolution sum. The difference is that instead of n we have used the continuous time variable. Okay, and instead of summation we have used integration. So this is the similar symbolic representation of convolution. Okay, so now let's see with an example. We are given xt as e to the power minus at ut and st as ut. So what is it? Minus infinity to infinity x of tau h of t minus tau dt. Oh, sorry, d tau. So for t less than 0, these both functions do not exist. Implies that y of t will be 0. Okay, and since the h of t minus tau do not is equal to 0 for t minus tau less than 0, then it is a causal system. Okay, so now let's check the convolution for t greater than equal to 0. So for t greater than equal to 0, y of t equals to 0 to t e to the power minus a tau d tau. Okay, so which when you solve you will get this. Okay, why we are multiplying ut here? Because ut just represents a function which one adds its value for t greater than equals to 0. So this is just to represent any signal. We use it in the standard forms to multiply ut or delta t or un delta n with these terms. Okay, so now let's see with the graphical interpretation. Similar process as for the convolution sum. First time reverse the signal, then shift it by t, and then integrate products of overlapping components. Okay, so now let's see within another example. Here input is 1 for t which is between 0 and 2t and 0 otherwise. Okay, and h of t is equal to 2 for t 0 to t, and t to 2t it is 3 and 0 otherwise. So this is h of t minus tau's graph, and it is x of tau's graph. So for t less than 0 there is no overlap. So now let's see for t which is between 0 and capital T. Okay, so this t will lie between 0 and capital T here. So you can see that you need to integrate the overlapping area only, which is this, and which is from 0 to t. and its value is 2 and its value is 1 dt. Okay, so for between t and 2t, okay, you need to break the limit as t minus t, and okay, so first we are taking it from 0 to t minus t, and then t minus t to small t. Okay, so this will be 3 for 0 to t minus t. Okay, the t minus t is this point, it is t minus t. Okay, so it is 0 for 0 to t minus capital T, it is 3, and from t minus capital T to capital is to small t, it is 2. Okay, so now let's see for 2t and 3t. The graph will look like this. Okay, so from this is again t minus capital T. Okay, so from t minus capital T, sorry, just wait, this is t minus 2t. Okay, it is t minus 2t. Okay, and it is from t minus 2t to this point. Okay, it is t minus t. Okay, so you can see that from t minus t to 2t it is 2, or from t minus 2t to t minus t it is 3. Okay, so you can compute the integral. Now let's see for 3t, where t lies between 3t and 4t. So the graph will look like this. Okay, here you need to integrate between t minus 2t and 2t, where the value is 3. So and for t greater than or equal to 4t, they do not overlap, so y of t is equal to 0. So this is the summary of the function yt, and you can represent it graphically also. Okay, so this was the two ways in which you can calculate the convolution sum and convolution integrals. One is mathematically and one is graphically. So there are certain functions which are easy to represent graphically, and I'll prefer them to solve graphically, because with the help of graph you can easily understand the overlapping area and solve the convolution. But there are certain functions which do not require graphical representation, or there are some functions which cannot be solved graphically easily. So you can solve them with the help of mathematical formulation, which I have told you. Okay, so this was all from my side in this tutorial. In the next tutorial we'll start with properties of linear time invariant systems. So thank you guys for watching. I'll see you in the next tutorial.